an example now. And this problem example is eccentric, symmetrical, bending for composite material. Okay. So I'm going to get this over. Right. So over here is the structure. So we are going to determine. There are two things that we would like to determine in this example. We're going to determine the largest or maximum stress okay. Determine the maximum stress for material 1, material 2, and then we also like to find the position of the neutral axis. Okay, the position of the neutral axis. So material 1, so on the left hand side, you'll see the cross-sectional view. Okay. Sorry, on the longitudinal view. So if you look at transformation, okay, on the right hand side, that's a cross-sectional, and the load is applied exactly at the red dot at the center over here. Okay, over here at the top end. Exactly at the center. Okay. So this is a composite material or sandwich. So I want you to take note that the horizontal part is what we always call the flange. Okay. And the vertical part is always what we call the web. Okay. So material 1 has a Young's modulus of 104 gigapascal. And then material number 2 has a Young's modulus of 200 gigapascal. Okay. So we are going to draw the free body diagram first. Okay. So we're going to sketch the free body diagram. Before we go on, if we label this point A and over here point B, right? We know for the fact that failure will occur at point A. Okay. And this is because of the bending moment, right? Maximum that bending moment will be at point where? Point A, right? So from here, we are going to sketch our free body diagram. So we know that this is our X, and this is our y, and then we have our rotation in a z, right? So we understand that based on our free body diagram, right, we have two components, okay? So over here, we will have I'm going to call it our bx, okay? So this is our bx, and then we know that we're going to have a by. Okay, we are aware of that. So on the left hand side, right, we will also know that there is a ax, right? And this ax over here will have a moment, right, at point A. Okay, so this is our point A, and this is our point B. Okay, and then we also have a load of force over here, right, known as our AY. Okay, but we are not going to consider AY, is because AY will not AY. Okay, I will put out AY will not generate normal stress. So we're going to ignore it for now. Okay. After the term test, when we do shearing stress, then we have to consider AY. For now, we know to consider AY. Okay. So, and another thing that we know, right? That we are we are aware of is there are two forces, which is your by and bx. Both by and bx, okay, so both by will generate moments about the z-axis. Okay, it will generate moment about z-axis. Okay, so by, right, by, the moment for by, so mz, so if we look at mz due to by, will be the length 2 multiplied by by. Okay, so because the length is 2 meters, okay, bx will be equal to bz is equal to the y bar. Okay, so the centroid, I'll define multiply by bx. So y bar is the centroid position from the top of the flange. Okay, so moment z, again, as I said, will be generated both, right, will be generated both by by and also due to bx. Okay, so this is the breakdown of the problem. Okay, so now the first thing we have to do, we have to know what formula to apply, right? So we understand that this is the structure is under eccentric, okay, symmetrical bending. And why we make that decision eccentric is because the applied force or why is eccentric, is there is a axial load, right, which is your AX, okay, which is your AX over here, right? Why I'm focusing on AX? Because point A is where failure will occur, okay? And then we have the next one is we classify this as symmetrical, is because the moment or the bending moment, or there is bending moment about one axis only. For this case, the moment will be in the Z. Okay. Unsymmetrical, you need to have how many? Two. Okay. Symmetrical is only one. So we are aware that the general formula, stress X is equal to Px over A minus by mz over izz multiplied by y. Okay. So for now, let's do this stage by stage. Okay. So we are going to analyze composite material. Or before we go into composite material, we have to determine what is our By and what is our By and Bx. Okay, so we have to determine. Sorry, we have to determine. Yeah, we have to determine our By and Bx. So we have to determine our By or Bx and By. Right. So I'm going to get the diagram. Or not, you don't understand why I'm doing some stuff. Right, I'll string it down so you can see better. So we know that this will be our Bx. And this coming down over here will be our By. Okay, so we know from here Bx is equal to 10 times 10 to the power 3. So this is Bx cos 60. Okay, so Bx is equal to okay, 5,000 Newton. And it's going downwards. And we know that By is equal to 10 times 10 to the power 3. And then sine 60. Which is equal to 8660. 8.66 times 10 to the power 3 Newton. And it is working towards the right. Okay. So now we have this value. We are going to focus on the axial load. Okay. We're going to focus on the axial load. So I'm going to, I'm still going to copy the same diagram. Okay. So we are going to focus on determine our stress in the x direction, okay, due to the axial load. So axial load for our case, we are going to consider the load AX. Okay, so we know by BX, which is equal to AX, and AX is equal to what? AX is equal to 5 times 10 to the power 3 Newton. And the 5 times 10 to the power 3 Newton will generate tensile stress.